Hello everyone, let's study about electrostatic potential energy. It is defined as the work done in moving a test charge Q from infinity to another point to overcome the force of repulsion produced by the electric field due to source charge. What it means is that even though it looks a very big statement here, if we summarize this, what it means is that if we have a charge called as capital Q, if this is a source charge, and imagine we bring another charge called as small q, this is called as test charge or any charge for matter. This charge is being brought from infinity, and then we are trying to bring this charge from infinity to some point here. Let's assume that we bring the charge from that point to some point, say P here. Whenever the charge is being brought towards this source charge, whenever we bring it like this charge capital Q will push it away, because both capital Q and small q has same polarity. It will push it away. So we are doing work here. Whenever the work is done by an external agency, that work would increase the system's potential energy. Here also, the work done by us in bringing this charge from infinity to this point, that work done gets stored as the system's potential energy. The symbol for that would be U. Let's find out what is the potential energy of a system of two charges. To understand this, let's have a case where we have a charge small q1. Now this charge is being brought from infinity. So we bring it from infinity to this point. Let's call the point as some point A. Now in bringing the charge from infinity to point A, there is no need to do any work at all. Here no work is done. That is because when we bring the charge, there is nothing opposing the charge movement. So the work is done against an opposing force. Here nothing is opposing the charge movement. So in this case, the work done, if we call that work done as W1, then what happens here is that work done should be 0, because nothing is opposing the charge motion. I'll redraw this. So let us take a point A, and a charge q1 has been brought to this point. Let the work done to bring this charge from infinity be called as W1, and that is equal to 0. Now let us assume that we bring one more charge called as q2. Now this charge is being brought from infinity. Now here the charges q1 and q2 have same polarity. So here we need to do work to bring it here. Otherwise it's a repulsive force, so we should do work. So let us assume that we bring it from here to this point. So apparently we have brought the charge to this point B, and the distance between point A and point B is r. So here I want to find out what is the system's potential energy when q1 and q2 assemble like this. So distance between them is given as some r. Now what I'll do here is, we will assume that this charge is somewhere here, at a point C, such that the distance between point A and point C is some x. So C is a random point. C could be taken anywhere. We taken C somewhere this side. Let us move this charge from point C to some point D, and this is a very small displacement. It's not very big in the diagram, but it's a very small displacement. Now in moving the charge from point C to point D, we are doing some work, because this q1 will push q2 away. So apparently q2 is here, we are moving it from point C to point D. In moving it, we are doing some work. Let us call that work as dW. Keep in mind that When the point C is at infinity, then the value of x would be infinite. When the point C, that is when the charge is brought to point B, then x becomes r. R is fixed because you want to find for this distance only, while x is variable. The work done to move from here to here would be F applied into dx, where F applied is a force what applying here. This is F applied. But this F applied is basically used to counterbalance. It is used to counterbalance the force of repulsive between the two charges, and that force is the Coulomb force. So the force what apply here, the F applied force, that is equal to the Coulomb force in magnitude but in opposite direction, because the Coulomb force will push it away. This is what is the Coulomb force. So in that case, the angle between dx and F Coulomb would be 180 degrees. There's also cos involved here, so we can write as cos theta. So the angle between F Coulomb and this would be 180 degrees. So in that in mind, this work done, which is dw, that is equal to F Coulomb would be k q1 q2 by x into cos 180 is minus, so it becomes a minus. So minus k1 q2 by x square becomes a force, where k is equal to 1 by 4 pi epsilon naught. So this is the work done form into dx. This dx already here. Now let us find the total work done. Now here dw is the work done to move from point C to point D, but we are moving the charge from infinity, so we're moving from here to here and then here and then here. So there is work done dw, there is dw work done. So for every small incremental movement, it's a very small incremental movement, for every small movement some work has been done and we need to add it. So the total work done in this case would be adding all the small amount of work done, that is equal to minus of k q1 q2 by x square dx. Here the variable of integration is x. The limits of x are from infinity to r. Now in this case, the work done is equal to here minus k q1 q2, a constant that comes out, and what remains is integral of x power minus 2 dx infinity to r. This remains, and that is equal to minus k q1 q2. This is of the form x power minus 2 plus 1 by minus 2 plus 1. The limits are between infinity to r. Minus 2 plus 1 would be minus 1, and this minus and this gets cancelled. That is equal to, it will be k q1 q2. It becomes x power minus 1, that is 1 by x, and the limits are pending. The limits are from infinity to r. Putting the limits here, what we get is, it is k q1 q2 by 1 by r minus 1 by infinity, that is equal to k q1 q2 by r. So this is the work done, but the work done is stored as potential energy. Therefore this work done is transformed or is seen as potential energy, and that is equal to k q1 q2 by r. So this is the expression for the system's potential energy. Now here we need to put with polarity. So if both q1 and q2 are positive, then u is positive. So the value of u can be positive, could be negative, could be 0 also. So u could be positive, negative, or 0. U is positive when both have same polarity, that is when both are positive or both are negative. In that case u becomes positive. U is negative when any one is negative. So either q1 is positive and q2 is negative, or other way around. If any one is negative, u becomes negative, and u is equal to 0 mathematically when R tends to infinity, because putting Q1, Q2, 0 is meaningless. So U is 0 when R tends to infinity. So when the charges are very, very far away, then they will not interact. Do you understand that? This energy arises because of the charge interaction. So the charges are interacting among themselves, and that interaction is seen as energy. If the charges are very far away, they will not interact at all. In that case, there is no energy. Now, positive energy means the system's energy is increasing, which means you have to be doing work here. So, when both are positive, we need to push it. So, we are doing work here. When both are negative, the same thing here also. Here, we are pushing it. So, we are doing work here. So, whenever work is done by an external agency, the system's energy will increase. That means U is positive. U is negative means the system itself does work. To understand this, it is possible when both are having different polarities. For example, here, when it is positive and negative, if you think this is fixed, for example, this charge will pull it on its own. So here, the system itself does work. Similarly, if this is negative and we place a positive charge here, then even in that case also, it will pull this. So whenever system itself does work, the energy is negative. And energy, as you know from high school, it is measured in joule. This is what is the system's potential energy.